Hi everyone, this is Srikanth, Assistant Professor of Triple Department. In this session, I am discussing the problems on bipolar junction transistors. A common base transistor amplifier has an input resistance of 20 ohms and output resistance of 100 kilo ohms. The collector load is 1 kilo ohm. If a signal of 500 millivolts is applied between the emitter and base, find the voltage amplification. Assume alpha AC to be nearly 1. Here is the emitter, base, collector transistor, and here is the input which we are giving 500 millivolts, and R input is 20 ohms, R output is 100 kilo ohms, and RC is equals to 1 kilo ohm. Here the input current IE is equals to whatever the input voltage which we are giving, that is 500 millivolts divided by RIN is 20. 500 millivolts by 20, which is 25 milliamperes. Since alpha AC is nearly 1, the output current IC is equals to IE, which is equals to 25 milliamperes. So the output voltage V output is equals to IC into RC. That is 25 milliamperes into 1 kilo ohm, which is equals to 25 volts. That is 500 millivolts is converted into 25 volts. And the voltage amplification AV is equals to V output by signal voltage, that is 25 by 500 millivolts, which is equals to 50. In a common base connection, current amplification factor is 0.9. If the emitter current is 1 milliampere, determine the value of base current. Here, current amplification factor alpha value is given and IE value is given. So, when these two values are given, alpha is equals to IC by IE. From this equation, we can take it as IC is equals to alpha into IE, which is equals to 0.9 into 1, which is 0.9 milliamperes, where IE is equals to IB plus IC, where IB is equals to IE is 1 milliampere minus 0.9 milliamperes, that is equals to 0.1 milliamperes. In a common base connection, alpha is equals to 0.95. The voltage drop across 2 kilo ohm resistance, which is connected in the collector, is 2 volts. Find the base current. Here IC is equals to 2 volts by 2 kilo ohms, that is equals to 1 milliamperes, where alpha is equals to IC by IE, where IE is equals to IC by alpha, which is equals to 1 by 0.95, which is 1.05 milliamperes. By using the relation IE is equals to IB plus IC, where IB is equals to IE minus IC, that is 1.05 minus 1, which is equals to 0.05 milliamperes. For the common base circuit shown in figure, determine IC and VCB. Assume the transistor to be of silicon. Here RE value is given as 1.5 kilo ohm, RC value is given as 1.2 kilo ohms, VCC value is given as 18 volts, VE value is given as 8 volts. Here the transistor is of silicon transistor. So base to emitter junction voltage is 0.7 volts. By applying Kirchhoff's law to the emitter side loop, that is here if we apply KVL in this loop, VEE is equals to IE into RE plus VBE. From this, IE is equals to VEE minus VBE by RE, where VEE value is 8 volts, 8 minus VBE base to emitter junction value because it is a silicon transistor, that is 0.7 volts divided by 1.5 kilo ohms, that is equals to 4.87 milliamperes. Here where IC is approximately equals to IE, that is equals to 4.87 milliamperes. And now in order to calculate the VCB, if we apply Kirchhoff's law to the collector side loop, we will have VCC is equals to IC into RC plus VCB, where VCB is equals to VCC minus IC into RC, that is 18 minus 4.87 milliamperes into 1.2 kilo ohms, that is equals to 12.16 volts. Now find the alpha rating of the transistor shown in figure. Hence determine the value of IC using both alpha and beta rating of the transistors. Here IB value is 240 microamperes, IE value is 12 milliamperes, where beta is equals to 49. Here alpha is equals to, when beta value is given, alpha is equals to beta by 1 plus beta, that is 49 by 1 plus 49, which is 0.98. The value of IC can be found by using either alpha or beta rating, as under IC is equals to alpha into IE, that is 0.98 into 12 milliamperes, which is equals to 11.76 milliamperes. And we can also write this one as IC is equals to beta into IB, that is 49 into 240 microamperes, which is equals to 11.76 milliamperes. Here a transistor is connected in common emitter configuration, in which collector supplies 8 volts and the voltage drop across resistance RC connected in the collector circuit is 0.5 volts. The value of RC is 800 ohms. If alpha is equals to 0.96, determine the collector to emitter voltage and base current. Here collector to emitter voltage VCE is equals to VCC minus 0.5. VCC minus 0.5, that is equals to 8 minus 0.5, which is 7.5 volts. This is our first voltage, that is collector to emitter voltage. And the next one is we need to calculate the base current. For calculating the base current, first here the voltage drop across RC is 0.5 volts. So the IC is equals to 0.5 by 800, which is equals to 5 by 8 milliamperes, that is 0.625 milliamperes, where beta is equals to alpha by 1 minus alpha, that is 0.96 by 1 minus 0.96, which gives us the value as 24. Now IB is equals to IC by beta, where IC is equals to 0.625 divided by 24, and this value is 0.026 milliamperes, or we can also write it as 26 microamperes, because generally the base current value is less as compared with the collector current and emitter current. And a NPN transistor at room temperature has its emitter disconnected. A voltage of 5 volts applied between collector and base. With collector positive, a current of 0.2 microamperes flows. When the base is disconnected, the same voltage is applied between the collector and emitter. The current is found to be 20 microamperes. Find alpha IE, find alpha IE and IB when collector current is 1 milliamperes. Here it is open circuited. In this case, what is the current which we need to calculate, and when it is open circuited, and what will be the currents we need to calculate. Here ICB0 is given as 0.2 microamperes, and here ICE0 is equals to 20 microamperes, which is given, where ICE0 is equals to ICB0 by 1 minus alpha, that is 20 is equals to 0.2 by 1 minus alpha, where alpha is equals to 0.99, where IC is equals to alpha into IE plus ICB0, where IC is equals to 1 milliamperes, that is equals to 1000 microamperes, that is alpha is equals to 0.99, and ICB0 is equals to 0.2 microamperes. Here from this, IE is equals to, that is 1000 microamperes is equals to 0.99 into IE plus 0.2 microamperes, that is equals to IE is equals to 1000 minus 0.2 by 0.99, which is equals to 1010 microamperes. The base current is equals to IE minus IC, that is equals to 1010 minus 1000, which is equals to 10 microamperes. The collector leakage current in a transistor is 300 microamperes in a common emitter arrangement. If now the transistor is connected in common base arrangement, what will be the leakage current, given that beta is equals to 120, where ICE0 is equals to 300 microamperes and beta is equals to 120, alpha is equals to beta by beta plus 1, which is equals to 120 by 120 plus 1, which is equals to 0.992, where ICE0 is equals to ICB0 by 1 minus alpha, where ICB0 is equals to 1 minus alpha into ICE0, that is equals to 1 minus 0.992 into 300, which is equals to 2.4 microamperes. Note that leakage current in common emitter arrangement is much more than in common base arrangement. For a certain transistor, the base current is 20 microamperes, collector current is 2 milliamperes, and beta is equals to 80. Calculate ICB0, where IC is equals to beta into IB plus ICE0, that is 2 milliamperes is equals to 80 into 0.02 plus ICE0, where ICE0 is equals to 2 minus 80 into 0.02, which is equals to 0.4 milliamperes, where alpha is equals to beta by 1 plus beta, which is equals to 80 by 80 plus 1, that is equals to 0.988, 0.988, where ICB naught is equals to 1 minus alpha into ICE naught, that is equals to 1 minus 0.988 into 0.4, which is equals to 0.0048 milliamperes. Determine VCB in the transistor shown in figure. The transistor is of silicon and has beta is equals to 150. Here VBB is given as 5 volts, RB is given as 10 kilo ohms, RC is given as 100 ohms, and VCC is given as 10 volts. If we apply Kirchhoff's voltage law to the base to emitter loop, we have VBB minus IB into RB minus VBE, which is equals to 0, where IB is equals to VBB minus VBE by RB, which is equals to 5 minus 0.7 by 10 kilo ohms, which is equals to 430 microamperes, where IC is equals to beta into IB, that is equals to 150 into 430 microamperes, that is equals to 64.5 milliamperes, where VCE is equals to VCC minus IC into RC, that is 10 minus 64.5 milliamperes into 100 ohms, which is equals to 10 volts minus 6.45 volts, which is 3.55 volts, where VCE is equals to VCB plus VBE, where VCB is equals to VCE minus VBE, which is of 3.55 minus 0.7, which is 2.85 volts. Now for the circuit shown in figure, draw the DC load line. Here the collector to emitter voltage VCE is given by VCC minus ICRC. Here is the VCC 12.5, RC value is 2.5 kilo ohms. When IC value is 0, then VCC is equals to VCE, that is 12.5 volts. And this locates the point of load line on the collector to emitter voltage axis. That is, when VC is equals to 0, then IC is equals to VCC by RC, that is 12.5 by 2.5 kilo ohms, that is equals to 5 milliamperes. In the circuit diagram shown in figure, if VCC is equals to 12 volts and RC is equals to 6 kilo ohms, draw the DC load line. What will be the Q point if zero signal base current is 20 microamperes and beta is equals to 50? Here VCC is 12 volts, RC is 6 kilo ohms. Here the collector to emitter voltage is given by VCE is equals to VCC minus IC RC, where when IC is equals to 0, VCE is equals to VCC is equals to 12 volts. This locates the point B of the load line. When VCE is equals to 0, IC is equals to VCC by RC, that is 12 by 6 kilo ohms, that is equals to 2 milliamperes. This locates the point A of the load line. By joining these 2 points, load line AB is constructed, that is 12 volts and 2 milliamperes. And zero signal base current IB is equals to 20 microamperes, that is nothing but 0.02 milliamperes. And current amplification factor is 50, where IC is equals to beta into IB, that is 50 into 0.02, that is 1 milliampere. Now zero signal collector to emitter voltage is VCC minus IC into RC. That is 12 minus 1 milliampere into 6 kilo ohms, which gives us 6 volts. Now the operating point is 6 volts and 1 milliampere. The next one is determine the Q point of the transistor circuit shown in figure. Also draw the DC load line given beta is equals to 200 and VBE is equals to 0.7 volts. Here the data given is VBB is 10 volts, RB value is 47 kilo ohms, RC value is 330 ohms, VCC is equals to 20 volts. Here VBB minus IB into RB minus VB is equals to 0, where IB is equals to VBB minus VBE by RB, which is equals to 10 minus 0.7 by 47 kilo ohms, which is equals to 198 microamperes, where IC is equals to beta into IB, that is 200 into 198 microamperes, that is equals to 39.6 milliamperes, where VCE is equals to VCC minus IC into RC, which is equals to 20 volts minus 39.6 milliamperes into 330, which is equals to 20 minus 13.07, which is equals to 6.93 volts. Therefore, the Q point is IC is equals to 39.6 milliamperes and VCE is equals to 6.93 volts. The DC load line, in order to draw the DC load line, we need two endpoints. That is VCE is equals to VCC minus ICRC, where IC value is 0, so VCE is equals to VCC. That is 20 volts and 60.6 milliamperes. So here 6.93 volts and 39.6 milliamperes. And when VC is equals to 0, IC is equals to VCC by RC, that is 20 by 330, that is 60.6 milliamperes. This is the IC value. This is the 60.6 milliamperes. This locates the point A of the load line on the collector current axis, that is VCC is equals to 20 volts. Now for a single stage transistor amplifier, the collector load is RC is equals to 2 kilo ohms and the input resistance is 1 kilo ohm. If the current gain is 50, calculate the voltage gain of the amplifier. Here the collector load is RC is equals to 2 kilo ohms, input resistance is 1 kilo ohm, current gain is 50, where voltage gain AB is equals to beta into RAC by RI, where beta is equals to RC by RI, that is equals to 50 into 2 by 1, which is equals to 100. Now determine the values of VCE off and IC saturation for the circuit shown in figure. Here VCC minus ICRC minus VCE minus IC into RE plus VE is equals to 0, where VCE is equals to VCC plus VE minus IC into RC plus RE. We have VCE offset when IC is equals to 0. So when IC is equals to 0, VCE offset is equals to VCC plus VE, that is 12 plus 12, that is 24 volts. When we have IC saturation, when VCE is equals to 0, IC saturation is equals to VCC plus VE by RC plus RE, which is equals to 10.67 milliamperes. In this session, we have discussed several problems on transistor circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.